So let me see. Yes, it's working now. So I told you how to write the electronic configuration of different atoms. So first of all, what you are going to write is 1s, 2s, 2p, 3s, 2p, 3s, then 3p, then 3p, after 3p you have a 4s, and you write 3d, something like this. But somewhere in the book you might see they write 3d here and 4s here, so that's okay. But always the electron are filled like this: 1s2, 2s2, 2p6, 3s2, 3p6. Then you need to fill the 4s first, and then you go to the 3d, yeah? And then 4s2, and then 3d, 1, 2, 3, 4, 5. How many electrons are there? Yeah? So this is the order. So yesterday evening I posted one slide, and in that one I filled the electron up to copper or something like that. So you just go through that, and you're good. So just like this. So let's say you have a hydrogen. So hydrogen have one electron. So up to that only, one is one, right? Done. Now in helium you have two electrons. That's it. So all we don't need these ones, these spaces, yeah. And then lithium we have three electrons. So two here, one here. We don't need all these things here, these things, yeah. And then beryllium we have four electrons. So we can put 4 here, like this, 2, 2. We don't need all these things, right? These are the empty spaces. And then boron, we have 5 electrons. So we put 1 here, 2, 2, 4, 1, 5 here. And then carbon, we have 6 electrons. So we can put 2 here, 2, 2, 2, 6, right? And nitrogen, 7 electrons. So you put 3 here. That's for nitrogen, yeah? Then oxygen, you have 8 electrons. So put 4 here, 2, 4, 4, 8. And then fluorine, 9 electrons. So 2, 2, 4 is gone, 5 here. Yeah, fluorine. For the neon is number 10, so 10 electrons. So 2, 2, 4 is gone there, 6 here. So that's a neon. So keep putting, yeah. And then sodium, there are 11 electrons. Now up to this is 10. Now put 1 here. That's sodium. Make sense? After sodium comes magnesium. Magnesium is 12. So put 2 here, and that becomes 12, right? And then aluminum. So this is full. Now aluminum has 13 electrons. Put 1 here. Now it becomes 13, right? So just keep doing that. So I did this yesterday and put in the practice slide. So I all feel just read it. Yeah, good. So like that one. So this is how we fill the electron, and I told you take extra care while you are working with the copper and chromium. Yeah, it's copper and chromium. So S orbital can have only 2 electrons. P can have 6 because P are Px, Py, and Pz. So 2, 2, 2. So P can have 6 electrons, and D can have 10 electrons. So D can have 10 electrons. So because D has 5 orbitals: dxy, dxz, dyz, dx square, y square, and dz square. So 1, 2, 3, 4, 5. So this has 2, this can have 2, this can have 2, this can have 2, this can have 2. So D can have up to 10 electrons. One orbital cannot have more than 2 electrons. Make sense? So according to the Pauli's exclusion principle or something like that, one orbital cannot have more than 2 electrons. So this is very important. It will be in exam. It is in homework too. So now I'm in the slide number 9. So this is effective nuclear charge. So this is very important. Effective nuclear charge. Nuclear charge. Effective nuclear charge. Sometimes they call estimated effective nuclear charge or something like this. So let's say you write a electronic configuration like this: 1s2, 2s2, 2p3, like this. So this is the second orbital electron. These are the second orbital. 2 is a principal quantum number. This is also principal quantum number, right? So this is basically 2, 2, 4, 47. Number 7 is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. So this element is nitrogen, right? So nitrogen looks like this. If you go here, neutron, proton is here. So proton is 7, proton is 7, because there are 3 to 5 to 7 electron, meaning that there are 7 protons here. They have positive charge. And then in first orbit, we have 2 electrons. In first orbit, 2 electrons, right? 1s2 means this first orbit. Now in the second electron, I have how many electrons here? 3 and 2, 5 electrons. 1, 2, 3, 4, 5 electrons like this. So proton has positive charge here, proton has positive charge here, electron has negative charge here. So how much force is this negative electron is experiencing from this positive charge, right? So that's called the effective nuclear charge. The effective nuclear charge is in center. There is a proton. There are protons. Protons has positive charge, and those protons are attracting all electrons toward it. And we are talking about the electron attracted by the outermost electron attracted by the proton here. So the force experienced by this outermost electron, this one of those outermost electron by this positive charge is called effective nuclear charge. Make sense? Good. So what is the effective nuclear charge? How do we calculate it? So it's calculated like this. Z star, either they write Z star or they write ZEFF, Z effective. So the force experienced by this electron from this proton is calculated as number of proton minus number of inner electrons. So like this. Yeah. How many protons are here? There's a 7 proton here. Atomic number of nitrogen. Nitrogen is 7. So there are 7 protons here. So how many inner electron here? So this is not inner electron. 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 Inner electron are only 2 here. 1, 2. So minus 2. So this is 5. So 5 unit force is experienced by these of the outermost electron here. This is called effective nuclear charge. Make sense? Good. Now let's calculate effective nuclear charge in what I have here is lithium. So let's say effective nuclear charge in lithium. What is the atomic number of lithium? Look at the periodic table I posted there. So hydrogen, helium, lithium. Lithium is number 3, right? So number 3. So in center you have a proton. There are 3 protons here in center. So and then lithium has 3 electrons. So 2 electrons goes in the first orbit, and then in outermost orbit there is 1 electron. We always put 2 inside and this in the other side, like this. And then what is the force experienced by this electron from these protons? So that's called effective nuclear charge. Effective nuclear charge is equals to number of proton is 3 minus number of inner electron is 1, 2, right? 2. So that is 1. So if force experienced by the outermost electron of lithium is 1. You could also write this another way, like this. So you could write 1s2, 2s1. So 1s2 is, these are 2 electrons. So this is the outermost electron. So, yeah. So you can write this way also. What is the force experienced by this electron? So there are 3 protons, and these are inner electron. Inner electron is 1s2. So I subtract this, and that is 1. So either way is good. Make sense? Good. Now let's look at another beryllium. Hydrogen, helium, lithium, beryllium. So beryllium is hydrogen, helium, lithium, beryllium. Beryllium is 4. So there are 4 protons here. So inside is 2 electrons, outside are 2 electrons, 4 electrons, 4 protons, right? Like this. Now, what is the effective nuclear force experienced by these 2 electrons? That is, number of proton is 4. Number of proton is 4 minus number of inner electron is 2. So that is 2 unit force. Yeah. So the force experienced by outermost electron is 2. Now let's talk about the boron. Boron is number 5. So there are 5 protons and 5 electrons. So 2 are here, 1, 2, 3 electrons are here. So if you look at the electronic configuration, it looks like this: 1s2, 2s2, 2p1. So this 2s you see 2 and 2. The second orbit electron are 2s2 and 2p1. So there are 3 outer electron, 2 outer inner electron here. So for boron, so ZEFF is we have 5 proton, and then these are the 2s2 and 2p1 are these electrons, these 3 electrons. So the force experienced by this electron is 5 minus the inner electron. So inner electron is this. So that is 5 minus 2 is 3. Make sense? So number of proton minus the number of inner electron is called the effective nuclear charge. So so let's look at slide number 11 and aluminum. I'm calculating the so I'm in the slide number 11, yeah. So slide number 11. So I'm calculating the effective nuclear charge for aluminum. So aluminum is number 13, right? Aluminum. If you look at periodic table, aluminum is in the 13th box. So it's a proton is also 13, new electron is also 13, right? Yeah. Good. Now let's. You can write the electronic configuration. 1s, 2s, 2p, 3s, 3p, like this. You can do like this, or you can draw something like this. Like this. Either way is the same thing. So 1s2, 2s2, so 2 to 4, 4, 6. How many? 13. So 6 to 8 to 10, and I have 2 here, and I have 1 here. So like this. So I'm working with the this is a proton, 13. So in the proton are 13 proton there, and the first orbit there are 2 electrons. In the second orbit you can put 8. 1, 2, 3, 4, 5, 6, 7, 8, like this. You see here, this is a second orbit. So 2s2, 2p6 is the second orbit, and then in the third orbit, there are 3 electrons. 2 here, 1 here. So 1, 2, 3, like this. Yeah, make sense? So that's how it works, right? Now, what is the effective nuclear charge here? ZEFF equals to number of proton. We have 13, and the number of inner electron is these and these are number of inner electron, right? So basically we are talking about the effective nuclear charge here in this orbit. So inner orbit we have 2 electron here, 8 here, 8 to 10. So 10. Or you can count here also 6 to 8 to 10. So these all are inner. So this 3 third orbit is outer. So 13 minus 10 is 3. So effective nuclear charge experienced by outermost electrons of aluminum is 30. Sorry, is 3. Make sense? Good. So in the next one, I wrote the silicon. Silicon is 14, but mistakenly I wrote 13p there. That's not 13p. That's a 14p. Yeah. So let's look at the silicon. Silicon. So silicon has 14 proton. That's number 14 box. There are 14 proton. So here in the center there are 14 proton in silicon and 14 electron. So 2 here, 8 here, 1, 2, 3, 4. 4 electron here, like this, right? 14 electron. So if you draw the electronic configuration, the electronic configuration of it looks like this: 1s, 2s, 2p, 3s, 3p, 4s. I don't know. 3D, something like that, right? Now we are going to fill the electron. So we have 14 electron. So 14 electron. So I put 2 here, 2 here, 6 here, 10. Now 2, 12. Now I can put up to 6 here. So I already have 2, 2, 4, 6, 10, 12 to 14, right? Is it 14? Yeah, now it's 14, right? Make sense? So always we do that one. So I don't need this spaces. I just remove this one. So I'm just talking about the force experienced by these electrons, third orbit electrons. So this is third orbit, this is third orbit, right? Third orbit. So third orbit, how much force third orbit electron experience? ZEFF, we have total is 14. So if you count the total number of electrons, 2, 4, 6, 4, 10, 2, 12, 2, 14. So number of electron and number of proton is same, right? So 14. So we have 14 proton here, number of proton minus how many number of electron I have inside. So inside is 2, 6, 8. So if you count 10. So if you count here 6 to 8, 8 to 10, 10. So if you count here 1, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So like that. So 14 minus 10 is 4. So the force experienced by outermost electron of silicon is 4. Make sense? So in aluminum, they are experiencing 3 unit force, but in silicon, they are experiencing 4 unit force. Make sense? So they are being pulled with more force in silicon than in aluminum. Yeah? Good. So like that one. So I will talk about this size later. So let's skip this 11 and 12 slide at this moment. Yeah. So in 11 and 12, I'm just talking about the size of the atom. We will talk about the size of the atom in the separate slide later. Yeah. Good. So you know how to calculate the effective nuclear charge, right? So effective nuclear charge experienced by outermost electron is equals to number of proton minus the number of inner electrons. Good. Now let's go to the slide that I posted yesterday evening. This is not a practice slide. This is a lecture slide. So it's a lecture 2 file. So how many electron we can put in the orbit, right? So that's the I'm discussing in slide number 1. So let's say we have first orbit. So there are neutron and proton here, neutron, proton in the nucleus. So this is the first orbit, n equals to 1 orbit. So this is n equals to 2 orbit. This is n equals to 3 orbit. 3 orbit. This is n equals to 4 orbit. N equals to 4 orbit. So in atom, how many electron I can put in first orbit? So that is given by the equation 2n square. This is the number of electron. How many electron we can put in certain orbit? So n is 1. So n is equals to 1. So 2 multiplied by 1 square is equals to 1 square is 1. 2 multiplied by 2. So in the first orbit, you can only put 2 electrons. No more than 2 electrons. Make sense? So that we have been already doing this kind of thing, but we just want to teach how they are putting here. So 2. How many electron I can put in second orbit here? So let's say this is first orbit, right? Now let's say in the second orbit. So when it goes to 2, let's put 2 here. So 2, then I have this 2 here, 2 square. So that is 2 square is 4. So 2 multiplied by 4 is 8 electrons. So how many electrons I can put in the second orbit? If I have enough electrons, I can put up to 8 electrons. Make sense? So this is a house where we can put 8 people. Yeah, like that. So this is 1, 2, 3, 4, 5, 6, 7, 8. 8 people. Any confusion? There is no confusion, right? So now, let's say how many electrons I can put in the third orbit. So I have this third orbit here. 1, 2, third orbit. How many electrons I can put in third orbit? So 2n square. So I look here if any message. No message here. All right. So 2. So I want to put how many electrons? So third orbit. So n is third. 3 square is like this, right? 3 square. So this is 2 multiplied by 3 square would be 9. So I can put up to 18 electrons in this orbit in n equals to third orbit. Make sense? Good. Now how many electrons I can put in the fourth orbit? So 2n square. So 2, if I put a fourth, I have a fourth orbit. So 1, 2, 3, fourth orbit. This is n equals to 4. How many electrons I could put in this big orbit, like a big house, right? So in a big house, we can put more electrons, right? So how many electrons I could put? So that's a 4 square. So 2, that's a 16. So I could put 32 electrons in the fourth house. Make sense? So that's how we calculate. Yeah? Good. So there are, I put the quantum number there basically, so how, you can just read yourself, yeah? So this is important. How many electrons we could put up to in certain orbit. N equals to, if we want to put the electron in first orbit, 2 electrons. In the second orbit, 8 electrons. In the third orbit, 18 electrons. In the fourth orbit, 32 electrons. In the fifth orbit, that could be 5 multiplied by 5 is 25. 25 multiplied by 2 is 50, right? In the fifth orbit, we could write 50 electrons. 50 electrons, yeah? In the sixth orbit, how many could we write? 6 square would be 36 multiplied by 2 is 72, right? So that's how it makes sense. Good. So already, so that many number of electrons we could put there. Now, let's go to the slide number 2. This is very, very important. This slide number 2 is really important. It's as important as electronic configuration. 2n square is not that, but it can be an exam, but 2n square is not that important. But electronic configuration, 1:2:2:2, 2p6, 3s2, 3p6, 4s2, 3d10. Those are very important, right? So this is as important as that one. Yeah, it's called the Hunts rule. H-U-N-T-S, Hunts rule. Hunts rule. H-U-N-D, Hunts rule. I think this is the name of a guy, maybe last name of the person, the Hunts rule. So this is called Hunts rule. Let's say I have something like this, 1s2, 2s, 1s2. So how does this, if I make a sheet, how does this look like? So let's say I have 1s1, like hydrogen is 1s1, right? Yeah, so it's always like this, 1s1, 1s2, 2s2, 2p6, 3s2, 2s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So it's looked like the electronic configuration is always that, never changed, right? So let's say this is a hydrogen, one electron is hydrogen. So how does this, if I make a sheet, what they call the box diagram, how does this look like? It looks like a box. This is a 1s orbital, right? Exactly, it doesn't look like this, but exactly the orbital look like this, but it's hard to, it's spherical, it looks like spherical, but we cannot draw the spherical in the paper, so we don't write like this, we just do the box diagram, yeah? How do I put that one electron in this box? So if it is a 1s sheet, 1s orbital, meaning orbital means sheet, right? If this is a sheet for this electron, how should I write? I should write like this, like this way. Make sense? It's a turning. So this is the electron sitting in the 1s orbital. Make sense? So this is basically, this has a spin. If you see something like this, this is the electron and it is spinning to the clockwise direction, like that. Yeah? Good? Good. So it looks like this. Now let's look at the 1s2. I want to draw for the 1s2. So this is a S is always one seat. So there are two electrons here, right? So if you write this one should be pointing like this, another should be pointing like this. Because in one seat you cannot have more than two electrons, and one is rotating to the clockwise direction, another is rotating to the anti-clockwise direction, right? Good. Now let's look at the so this is the 1s2 configuration. Now let's do another one. So I want to do other thing. There are no confusion. Let's do 1s2, 2s2, 2p3 configuration. So this is a nitrogen. This is a nitrogen, yeah. So so you already know how to put these two electrons here. So 1s2. So this is 1s sheet. This is 2s sheet. This is 2p seat. How many seats for the 2p? There are three, right? Px, py, pz. There are three seats for p, right? So p, you always have to cut into three boxes like this. P has three seats. So this one is px, another is py, another is pz. So this p is three seats. Yeah? Make sense? Good. So how many electrons I have here? So I have two electrons here, put like this, clockwise direction. This is anti-clockwise direction. These two are good. Now this one clockwise, another electron anti-clockwise direction. Now the problem comes here. How should we write this p electron in this p? This, let's say this is px, this is py, this is pz, right? So this p has three seats there. So how should we write the electron? First, you need to fill one by one. So first we must fill the electron 1, 1, 1, and then if there are leftover, and then only we start to put two together. Make sense? So that's called the Hunts rule. So put 1, 1 first. There are three electrons. So I put one here, I put one here, I put one here. Good. I'm good. I already put three electrons here. Now this is good, right? But if I put like this, instead putting like this one, if I put like this, let's say I have three seats like this. Let's say I put one here, and this is px, this is py, this is pz. If I put one here and I pair this here, and then I have these three, right? You see, I write this way. So this is completely wrong. In nature, it doesn't work that way. So first of all, you need to put electron 1, 1, 1, 1, 1, and then when you have extra, then you start to pair. Yeah. So this is called the Hunts rule. Make sense? Good. Now let's do some other. So let's do P1 here. So let's say somewhere is the electronic configuration is P1. How would I do that P? So there is no problem here. In these two, there are no problem, but in only P has a problem, right? So let's say P has 3 seats, 3 seats. So where should I put this electron? First box. How should I put this? Pointing upward, clockwise direction. Make sense? Now let's say I have a P2 here. Let's say I have a P2 here, P2. So how should I put that P2 electron here? I have 3 boxes here. First put 1, 1, 1. So this is Px box, this is Py box, this is Pz box. So this P is divided into three parts there. Now first, how many electrons do you have here? 3, 2, right? Now put 1, 1, 1 first. So how many? So you have 1. Now you have another. Now you have 2 electrons are gone. So this is empty here. Make sense? Yeah? But if you write this like this, if you write this like this, let's say you have 3 boxes here, is 1 here, and another electron here. Now these 2 are empty. Now this is Px, this is Py, this is Pz. This is wrong. This is completely wrong. You cannot put, if there is a space, more space, it's just like that there are 2 friends and there is 1 seat, right? And if you are in 1 seat, 2 people 1 seat, that's bad. So if there are a seat, you should not squeeze together. You should sit 1 by 1 in each box, social distancing, right? But if there is no seat, what should we do? We should squeeze two together. Yeah? Make sense? So it's like this. Yeah. So now let's do P3. P3 we already did it. So if there is a P3, so you have to put 1, 1, 1, 1 first. Good. Now let's say you have a P4. What do we do? Now we don't have enough seat here. Now we start to squeeze 2 together, right? So I'm going to squeeze extra 1 here. Make sense? 1, 2, 3, 4. Yeah? Good? First put 1, 1, 1, 1. And if you have extra, then start to squeeze 2 together. Good. Now, let's say I have a P5 here. P5 here. What should I do? So I put 1, 1, 1, 1 first. Then I squeeze another 1 here. 1, 2, 3, 4. Now, but I have 5 here. So I squeeze 1 here. Like this. Yeah? So if the 1 electron is pointing up like this is a clockwise. Another electron must be anti-clockwise. Yeah? 2 electrons cannot sit in each box. 2 electrons cannot sit like this. 2 pointing up. Yeah? 1 is pointing up, another is pointing down. If 2 friends sit together, one must be looking other side, another friend must be looking the other. Yeah? Like that. This is the quantum mechanics. The electron behave so weird with, right? Now let's look at the P6, 2 P6. Let's say I have 2 P6, they have no problem here. What is the, so P have 3 seats like this. Now put 1, 1, 1 first. Now 3 are gone. Now you still have 3 more here, right? Now start to speed. 2 like this. So 2, 4, 6 like this. Yeah? 2 P6 or 3 P, anything. Yeah? So we have to do like this. Good. So if there are a P, so it doesn't matter whether it's a 2 here, a 3 here, 4 here, that's just the principal quantum number here. But when it comes to the electron, always distribute like this. This is called the Hunt rule. Yeah? Now let's look at a d orbital here. Did I did a d orbital here? I think, so I think in the next slide I have a d orbital. Let's look at d orbital in 4. So let's look at the slide number 4. Yeah? Let's look at the slide number 4. So, in slide number 4, if you see the manganese, so there is a manganese. The manganese has a 1, 2, 3, 4, 5 electrons. So in the last configuration, manganese is like this, 3d5, right? So you can write 1s2, 2s2, 2p6, 3s, 3p6, 4s2, 3d up to 3d10, right? Like that. So manganese has in the last sheet like this. So how many sheet D has? I told you D has 5 sheet, right? dx, dxy, dxz, dx square, y square, dz square, dx square, y square. So D has only 3 sheet. D has 3 sheet. This is px, py, pz. But D has 5 sheet. 2, 3, 1, 2, 3, 4, 5 sheet. 1, 2, 3, 4, 5 sheet. So if you want to name, you don't have to name it, but if you want to name this one, this is called dxy, this is called dxz, this is called dz, I don't know, dx square, y square, this is I don't know, dz square. So there are 5, dxy, dxz, dyz. This is dyz, like this. Yeah, there are 5 sheets. The d orbital is divided into 5 parts, right? And they can have, each have 2 electrons. Each sheet can have 2 electrons to make 10. So in D we can make up to put up to 10 electrons. Now we have how many electrons here? 5 electrons, right? Now put one by one first. So put 1, 1, 1, 1, 1, like this. This is good. But if you put like this is bad. There was a seat and you just squeeze here, you break the rule here. Make sense? So put 1, 1, 1, 1, and if you have extra, squeeze it. Yeah? So, make sense? Good. Now let's do that D6. D6. So this is D5. Now I want to do the D6 configuration. Let's say D6. How do I put it? First I put 1, 1, 1, 1, 1. 1, 2, 3, 4, 5. 5 I already put, but I still have one more electron, right? Now I need to squeeze one here like this. Yeah? D6. Make sense? Good. How about D7? So first put 1, 1, 1, 1, 1. There are 5. Now you put 1, 6 here, then you squeeze another one here. That's a 6, D7. Yeah? How about the D8? So put 1, 1, 1, 1. First 1, 2, 3, 4, 5. Now you have 3 more. 6, 7, 8. Like this. Yeah? Make sense? Easy. Now let's do D9. How does the D9 look like? First put 1, 1, 1. 1, 1, 1, 1, 1. 5. Now squeeze. 6. Squeeze. 7. Squeeze. That's 8. That's 9. Yeah? Now let's do one more. And then we are done. Now let's do D10. How do I do it? So I put 1, 1, 1, 1 first pointing upward like this. Like this. 1, 1, 1. Now I start to squeeze. I have 5, I already put it. Now 6, 7, 8, 9, 10. Now D is full. Yeah? D can have maximum of 10 electrons and D cannot have more than that. Make sense? Because we have 5 seats. Good. It's very simple actually. Put 1, 1, 1 and then if you have extra, just squeeze it to the 2. Yeah? So this is like that. Now let's go to that's Hund's rule. Yeah? So in Hund's rules, if there are the empty seat in the same cell, like a 3p, or in S there is no problem, only in the P, yeah, P and D. So in P and D, you need to put 1, 1, 1 first, and then if there are extra electrons, then you need to start to pair. It's a Hund's rule. Good. Now let's go to the slide number 5. So this is in homework, yeah. So I put the 5 choices there, and which one is wrong, and I put. So you just look where is the 1, 1, 1, or something like that, and then that's right. And if already paired before we need to pair, that's wrong, yeah. Good. Now atomic radius. What is the atomic radius? Atomic radius. Atomic radius. So I'm in the slide number 5, yeah. Slide number 5. So what is atomic radius? So basically atomic radius is like this. So this is an atom. Let's say this is a hydrogen atom. So this is a proton neutron here. What is the distance from this nucleus to the first this orbit? That's called the atomic radius. Make sense? So this is a hydrogen atom. What is the atomic radius of hydrogen? Basically, electron is in the first orbit, and this is the nucleus. The distance between the nucleus and the orbit is called the atomic radius, right? What is the radius of a ball? Just like that. What is the radius of a basketball ground or something like that? Yeah. So what is the radius of the circle from here to here? So that's called the atomic radius. From the nucleus, the outermost orbit, the distance between the nucleus and the outermost orbit is called the atomic radius. Yeah. So let's say I have a aluminum here. So aluminum is 13, right? 13. So what is the atomic radius of aluminum? So I draw proton neutron here at the center, proton plus neutron, and in first orbit I can put 2 electron. In the second orbit I can put up to 8 electron, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8 electron. And then in the third orbit I can write up to 18 electron, right? 3 square multiplied by 2, 18 electron. But I don't have that many electron. I already put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electron, but I have 13 electron. Now I can put 3 electron here, like this. Now what is the atomic radius of aluminum? So atomic radius of aluminum is distance from the center to the outermost, this third orbit. So this distance is called the atomic radius. Make sense? Yeah? So the distance from the nucleus to the outermost orbit is called the atomic radius. Yeah? So how do people measure it? So people measure a little bit different way. So this is how it is defined. So how do people really measure this one? So what they do is, let's say this is a chlorine atom and this is also chlorine atom. Two chlorine atoms are sitting together like this. So they have the same size actually. They have the same size. So if you have a chlorine molecule, so we could write Cl and Cl. So this is Cl atom, this is Cl atom. I have two Cl atom, right? Make sense? Two Cl atom. And what they do is, they measure from the center of this one to the center of this one. Center of this one to center of this one, right? And then they divide by 2 and they call the atomic radius. Basically, it's the same thing what I already told you. Yeah? So the distance between, this is called the homonuclear molecule. Homo means same, chlorine and chlorine. In homonuclear molecules, what they do is, they measure the distance between nucleus of one to nucleus of another. So for chlorine, this is 198 picometer, this distance from here to here is 198 picometers. So what is the atomic radius there? So the atomic radius of chlorine is atomic radius of chlorine is 198 divided by 2. That is 99 picometers. Make sense? It's the same thing basically. They are saying this is the distance from the outermost orbit to nucleus. Distance from outermost orbit to nucleus. Yeah. So what they do is, they take a homonuclear molecule ClCl and they measure the distance between the nucleus of these two atom and they divide by 2 and that gives the atomic radius. Make sense? Good. But how about if there are not the homonuclear molecule like this, let's say heteronuclear molecule, we have like the HCl or CCl or something like this. So let's say we have a heteronuclear molecule. This is a carbon, this is a chlorine. Let's say this is carbon and this is chlorine. So this is small, this is big, right? So how do we define the atomic radius of each of these one here? So previously from chlorine, you already find 99 picometer, right? For chlorine, it was 99 picometer if you look the previous paragraph, right? Now what they do is they measure the distance between this and this. So that distance is 176 picometer. But previously, according to a homonuclear atom, they already found this is 98. For chlorine, it was 99. So this was 99 picometer. So from here to here is 176. From here to here is 99. So from here to here would be, so for carbon radius of carbon or Cr, what the right is, so radius of carbon atom would be, so you already know total distance, that is 176, and then you already know the chlorine, that is minus 99. So that gives you 77 picometer. Make sense? So you can do the two ways, right? If this is a homonuclear, meaning that two atoms same, so you measure the distance between one nucleus to another nucleus and divide by 2. You get the atomic radius. But how about the heteronucleus, like carbon and chlorine, hydrogen and chlorine? So what they do is, they measure the distance from here to here, and from the homonuclear, already they know the radius of this guy, and they subtract from total to the known, and they calculate the radius of the other atom. Make sense? Good. So that is that. Now let's go to the slide number 6. So we are really moving fast. It's pretty simple. It's not like the quantum number or like the slide number, sorry, chapter 5. So it's pretty easy. It's not now, how does the size of the, so this is one, I think in the lab number 11 or somewhere, this is there also, yeah? So in Chem 106. So So look the periodic table. How does the periodic table look like? So if you go here, there is a hydrogen, there is a lithium, there is a sodium, there is a potassium, something like this, right? If you look the periodic table, look the periodic table I posted there, and it looks like this one. And if you go here, from here to here, beryllium, and then boron here, carbon, nitrogen, oxygen, fluorine, neon. So periodic table look like this, right? Look the periodic table look like this. And then the magnesium is here, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So if you look at the periodic table, they look like this. And here somewhere there are the D elements here. So which is big? So if you compare this, which is big? This is big, this is big, or this is big. So if you go down, it becomes big. Yeah. So potassium looks like this, big, very big, like this. The size of the potassium is very big. Yeah. And then so the sodium is size is a little smaller than this guy, and the lithium is little smaller than sodium, and then hydrogen is really smaller, like this. Make sense? So if we go in a group from top to bottom, what happens is size is increasing. Very small, a little bigger, very big. If you go further, it's a very, yeah. In a group, if we go from top to bottom, size of the atom becomes bigger and bigger and bigger, right? Make sense? So which is the biggest? Potassium is biggest. Which is the smallest? Hydrogen is smallest. Which is bigger between lithium and sodium? Sodium is bigger, lithium is, yeah? Easy. Now, how about this one? So if lithium is this one, so beryllium would look like a little smaller than this guy. So this is big, this is smaller. So this is very big. If you compare this and this one, this looks a little smaller. So this is bigger, this is smaller. Yeah? So if you see here, so from this is bigger than this one, but this is smaller than this one. Yeah? So if you go from top to bottom in a group, size increases. Size goes increasing like this. Yeah? But if you go from left to right, size decreases. Size decreases. So which is big? So boron would look like this, like this. Then carbon would look like smaller. The nitrogen would look like even smaller. Oxygen would look like even smaller, and fluorine would look like small, and neon would like this. Yeah, make sense? Easy. So if they are in the same row, the size of the atom becomes smaller, and smaller. Yeah. But if they are in the different row, like this, first, second row, third row, like this, very small, bigger, like this. Yeah. As you go down in the periodic table, size becomes larger and larger. But if you go in the period from left to right, the size becomes smaller and smaller. Make sense? So in this slide number 6, this is already size is written there. You can just look at and you can easily understand. Yeah. So from top to bottom, size is becoming bigger. If you go from left to right in the period like this, size is becoming small. Yeah, it's simple. Now, why this happens? So I put that reason there in the side note in slide number 6. So let's look that one. So I still have some time. So look that reason there. Why? Left to right, size decreases. So let's talk about here. So we have a lithium here. After lithium, I have a beryllium here. So why the size of this guy is very big like this? Size of the beryllium is very small like this. That's what we need to explain, right? So why that happens? So draw the atomic structure. So lithium. So what is the number of proton of lithium? Lithium is in number 3, right? Hydrogen, helium, lithium, number 3. So there are 3 protons, 3 electrons. So lithium. So I'm drawing the lithium first here. So lithium, it looks like this. So there are proton and neutron. So proton, there are 3, and the neutron, maybe there are 3 or 4, I don't know. So let's write 3 here. So I don't need that neutron here, so even I don't write proton 3. Now I have 3 electrons. So in the first orbit, I have 2 electrons. I cannot put more than 2 electrons in first orbit, right? I need to put only 2 in the first. And then there is another orbit. I'm going to write another electron in the second orbit. Now calculate the effective nuclear charge here. So what is the ZEFF? ZEFF. That's a proton is 3 minus inner electron is 2. So that is this electron is experiencing only one force from the proton, right? Make sense? Now let's draw the same thing for the beryllium. So beryllium is number 4. So number 4, beryllium is number 4. So proton are 4. In the first orbit, I'm going to write 2, 1, 2. In the second orbit, I'm going to write another 2, like this. Now, calculate the effective nuclear charge here, ZEFF. How much here? So proton 4, inner electron is 2. So that is 2. So force this electron experience? 2, right? How much this electron experience? Only 1. So these 2 electrons are being pulled in by this 4 proton more strongly. So this size, the size of this cell become small. Make sense? So this is big, this is small. Make sense? Good. So if you go further, so you have a lithium, beryllium, boron. So you have a boron here. So boron is number 5. So if you look at proton are 5, and then you put the 2 in the first one here, and then 3 in the another one. 1, 2, 3 in the another one. Now calculate the ZEFF. ZEFF would be a 5 proton minus 1, 2 electron. That's a 3. So each electron outside this electron experiences 3 unit force, right? So these electrons are being pulled very strongly toward the nucleus. Make sense? So this is this outer orbit becomes contracted like this. 1, 2, 3, like this. So this is very big. This is a little smaller. This is the smallest one. Make sense? So when the ZEFF value increases, the outermost electron are pulled strongly, and the size of the atom becomes small. Make sense? Good. So I'm just talking in the going from left to right. So let's talk about the going from top to bottom in a group. So I just finished going from left to right, right? Now let's talk about the going from top to bottom. So lithium, so you have hydrogen, lithium, sodium, and then, I don't know, maybe potassium. So let's look the hydrogen. How does the hydrogen look like? So I have 2 minutes, so let's finish this one. Hydrogen. So if hydrogen is number 1, so proton is number 1 here, and then first electron is in the first orbit like this. How about in the lithium? So in the lithium, hydrogen, helium, lithium. Lithium is number 3. So this is the first orbit. So proton 1, and then in the first orbit there are 2 electrons, right? And I have number 3. So I have 3 electrons. So I cannot put another electron here. I need to put the electron in another orbit. So there is only 1 orbit in the first hydrogen, but in lithium there are 2 orbits. So size of the second orbit is too big. So effective nuclear charge cannot explain this one. Yeah. So because the electron is being added in the extra cell there, right? Extra orbit. So how about here in sodium? How about here in sodium? So so this is the proton is 11. In sodium, proton number is 11. 2 electrons are here. Then 8 electrons are in the second. 2, 3, 4, 5, 6, 7, 8. And then I have still 8 to 10. Now I have another 1 electron, and I need to create another cell here. So that's too big, right? So when I go from top to bottom in each step, I need to put 1 extra orbit, right? So the size of the orbit is too big, yeah? So the size becomes increased. So effective nuclear charge is pretty much cannot do anything when you put the electrons too hard, yeah? So there is a reason, so that's how it is explained. Make sense? So with the help of this concept, we can explain other things. We have a couple of concepts in this chapter. We will we'll be discussing in the next class. Yeah. So thank you, everyone. So there is a homework in Canva. Don't forget to do homework. So I'm going to stop this one.